Okay, thank you for inviting me. Unfortunately, my voice became very bad this morning, so it may be a short presentation. Sorry for that. So here is my some of the talk. I think most of the people hear about the basics of the cryptography. Therefore, I will skip those parts. But cryptography is divided into symmetric key and asymmetric key encryption. And in symmetric key, we usually assume there are block ciphers, stream ciphers. And even if there is no key, we assume hash functions to be a part of symmetric key cryptography. And block ciphers are very important tools in symmetric key cryptography. They take a message input M and a K and produce an output C. Usually the message block and ciphertext blocks are M bit length and K is K bit length. And one of the most famous designs regarding block ciphers is iterated block ciphers. Usually we use a ground function G, which is assumed to be weak. But if we iterate it R times, then we assume that the system is secure, and it is very efficient usually in hardware. And we had an AES competition which ended at 2000. And after that competition, an block cipher algorithm is chosen to be a standard algorithm. And it was organized by NIST, and the most important evaluation criteria is, of course, security, but with the security also cost, algorithm, and implementation characteristics are important. And Randomness, designed by Raymond and Demon, won the competition and became AES. And the security algorithm is compared with the other algorithms. One of the criteria was the outputs of the algorithm should be indistinguishable from a random permutation. And other security factors also we considered, like differential cryptanalysis, linear cryptanalysis, and an algorithm is chosen. And here in this talk, I will talk about random sequences and how they are used in cryptography. So it's very difficult to define a random sequence. We give this sequence, but probably it's not correct mathematically, but a sequence whose terms are chosen from a finite set, which each term takes with n equal probabilities called random. So in cryptography, they are used in several applications: salts, primes, secret keys, and any challenges using a challenge response protocols. And also we have random number generators. We have true random number generators, TRNGs, and it's very difficult to use TRNGs because they use non-deterministic source to produce random numbers. And usually you cannot be sure that it is really a random number. Some examples in the literature use atmospheric noise or noise in electrical circuit or emission of particles. They are all used as TRNGs. But it is inefficient because also you cannot produce the same random number in another place. Therefore, pseudo-random number generators are used. They are not random, they are deterministic algorithms, but they assume to be random looking. So it's very difficult to define random looking also, because since they are periodic, they cannot be random. But they can take a random sequence seed, usually produced by an entropy source, and produce a periodic random looking, very long sequence. And in most applications, this seed is produced by TRNGs, but other sources can also be used. So we have some tools from statistics. One of them is statistical randomness test. So given a random sequence, we examine some properties of the sequence and try to conclude whether the sequence is random or not. This is called hypothesis testing. So for example, the number of ones in a binary sequence is one of the criteria. If there are few ones or few zeros in the sequence, we assume that the sequence cannot be random. Or the distribution of ambit templates like approximate entropy and several tests in this test suite. And as a result, a p-value between 0 and 1 is produced. And the details can be found in any statistical books. So why do we need statistical randomness tests? Actually, one test is not sufficient usually. For example, this sequence, as you see, there are few number of ones, so it is not random. But if you just write 0 to the first half and 1 to the second half, it is still not random, as you see. And you cannot use only frequency tests. Here you need block frequency tests to detect this one. Or this one is a classical example of non-random sequence because the number of runs is just too much. The number of runs is uninterrupted blocks of zeros and ones. And in the fourth one, the number of runs is also arranged, but this time a block 0, 1, 1, 0 occurs a lot in an overlapping template. 0, 1, 1, 0 here first, here another one. So this is also not random in that sense. So which means that you cannot use only one randomness test. You need test suite instead. And this test suite should also always include frequency tests, but some other tests. And there are some test suites in the literature. But the problem is that they are purely statistics. So there are some statistical test suites in the literature. And we want to apply, we want to understand whether our block cipher satisfies the security criterion or not. But it's not straightforward. We should find a solution to that problem. And this is also one of the problems in AES competition. And usually this is the normal procedure. First take a sample sequence from the set, then evaluate the set by randomness test. So in 2000, so during AES encryption standard, Soto proposed that we should take some non-random data like low weight data, high weight data, and some other data, and obtain a sequence, and by concatenating all of the sequence, therefore we have a very long sequence. We know how to test this long sequence by a statistical randomness test and find the results. But there are some problems here. First of all, if somehow we have some good tests which are designed to test random outputs of block ciphers or hash functions directly, it's better. So here is our motivation. Can we find a method which measures a collection of short sequences directly instead of concatenating them? But to attain this, we need to solve some difficult combinatorial problems because they are not straightforward. Usually in statistical randomness tests, some approximations are used, but they don't work very well for 128 bits or 2048 bits because they are too short to use approximations. Therefore, we need exact combinatorial formulas. So here's our motivations. And here I will talk about periodic template tests. And it was accepted in 2019. And there are also some other tests, for example, run tests, which is accepted in cryptography and communications. And we also finished work, which is already submitted to, again, cryptography and communications. And you can find the details. And I will leave this presentation here, so anyone who is interested can take the presentation, because I will not give all the details of the presentations. For example, I will state some theorems, but I will skip some proofs of the theorems. But in the presentation, you can find all the proofs as well. So we will have a case study here. So as I said, there are many statistical randomness tests for collection of short sequences. So the first one is periodic template test. So for this, we need to define template. So a pre-specified string is called template, for example. For this one, if you choose 0, 1, 0, you see that that doesn't exist any 0, 1, 0 subsequence. But this one contains 1. But this one contains twice this one and this one. And here is important, this one contains 5 because we choose it in overlapping. 0, 1, 0 is the first one. This is the second one, the third one, fourth one, and fifth one. And this is a very famous test in this test suite, but some approximations are used and some probabilities are stated there, but some of them are wrong, unfortunately. There are 2 randomness tests considering number of occurrences of a string, overlapping template test and non-overlapping template test. And in overlapping template test, a sequence is split into 124, but since the template is 9-bit long, 124 plus 8, 132 bits sequences. Then a classical chi-square group of fitness test is applied. But unfortunately, the first probabilities were wrong there. And Hamano et al. Corrected those probabilities with a combinatorial problem. They defined a combinatorial problem for that and solved that part. But that part was a little bit straightforward. But the problem is there that NIST corrected all the probabilities according to this template. But these probabilities are not valid for other templates. And it's not clear how to apply the overlapping templates for any other block. If you choose the block as 1, 1, 1, 1, so there is no problem. But if you choose any other block, then the test simply fails. So here is our method to evaluate probability calculations. So for that reason, we define a template. For example, this template has period 3. As you see, 0, 1, 0, 1, 0, 1 occurs 3 times. And this template has 0, 1, 1, 0. So if I add 1, 1 here, it will be periodic. So it has a period of 2. For this one, 0, 1, 1, 0, 1, if I add 0, 1 to the end, it will be periodic again. Therefore, the period has 5. The definition can be stated here, but it's not easy to understand what is the definitions correctly. And here is our problem statements. Very easy statement, but very difficult to solve it. What's the number of binary sequences of length n, which contain a given template row of length 9, for example, totally k times? And it's a difficult problem. Even if it seems easy, it's not that easy, but we have an easy case. What's the number of binary sequences of length n, which do not contain templates? So we have a way to solve this. First, we will need to solve this probability, and we will apply this method to the next question. So for that reason, we need some other definitions. Let an be the number of strings which do not contain row, and bn is the number of strings which contain row only once as an initial segment. So we have a very simple lemma, and the proof is also straightforward. For example, 2an is equal to an plus 1 plus bn plus 1, and we have the below formulation. So actually, as I said, if you add 0 or 1 to the beginning of the sequence, either it still does not have any template, or it contains the template, but only in the first place. Therefore, as a result, the first one, 2an, is equal to an plus 1 plus bn plus 1 is follows. But the second one, we need to think a little bit. This time, similarly, we obtain a neo string to the beginning. For example, this string does not contain this template, but we add to the first place. Then we see it contains 4 copies of row, starting at first, 4th, 7th, and 10th terms. So it gives us the formulation. I will skip those proofs. And let me show the statement again. This time AN is equal to BN plus something, but it depends on the lambda and the rho. And using this idea, we have a theorem, but here we need some generating functions to make it independent of the type of the template. So this is our basic theorem. And here fz is similarly 1 plus z rho, z to 2 rho up to that place. And I will skip the proof, but here is our important corollary. For any given template, this number only depends on the template, the length of period of the template. So if, for example, the length of the template is 9 and period is 3, there are many different templates for that one. The probability is same for all of them. So we need to evaluate different probabilities. And also to apply probability calculations, we need corollary. So anyone who takes string ciphers, I think, will know how to deal with that one. So if we are given generating functions, the denominator will give you the recurrence relation. Therefore, using that one, we can find these probabilities for all of them. And I will just give an example. For example, let us find the recurrence for this template, whose length is 4 and whose period is 3, because 0, 1, 1, 0, 1, 1, it makes the period 3. Therefore, fz is by definition 1 plus z cube. And if I write this generating function, we obtain this one. So we need to consider this denominator, which gives us the recurrence relation, where n k is the number that we are looking for, the sequence of length n, which has exactly k templates. And there are also some other examples. That part was mathematical part. We evaluate some mathematical calculations. And you can find the details in the paper, but how can we apply this test to a statistical randomness test to evaluate block ciphers? And it is straightforward. If you know chi-square test, we apply chi-square fitness test. First, we evaluate chi-square, very useful for from statistics. Then we evaluate p-value by incomplete common function. And we need to define a threshold. You can define other thresholds for other applications, but usually 0.01 is chosen as this threshold. So we apply this for many strings, but in order to publish it in a journal, you need to show that it really works for some other non-random data. And therefore, we produce some data which starts with this one, but if all the data starts that one, of course, it will pay for min test. So we choose this prefix is added for only 1 in 6 sequences. And later we showed that it passes from all of these overlapping template tests, but fails from our test. And here is very important contribution of our work, because this probability table is needed for NIST test suite, who use NIST test suite for overlapping templates test. It is not corrected. We send an email to Meltem, and I think they will show it. They will correct it soon. I didn't check for the last 2-3 months, but 3 months ago it was not corrected. And I have some conclusion, but before let me conclude this talk first. Here we evaluate the number of occurrences of fixed template in a sequence, and we use it as an indication of randomness of collections of sequence of length time. This is an important topic, but here this is also an interesting mathematical problem, and we observe that these numbers are same for any 2 templates in the same period. And we propose new family of statistical randomness tests, and we correct the probabilities for this test suite. But in this talk, before concluding it, I want to talk about future ideas. So to test the randomness of block ciphers, why is it important? Because, for example, if you design a block cipher, which is 20 rounds, you need to show that the exact round number where the randomness is very important in design. For example, you need to show that randomness is achieved in 6 rounds. Therefore, it is random, but which means that the first 5 rounds have non-random outputs. And it is normal because your round function is big. So in one iteration, it still remains big. But at some point, it becomes complicated and random looking. So it's very important, but it's also important to use some properties of block ciphers. For example, strict avalanche criteria, propagation criteria, characteristic criteria, or if you apply using hash functions, coverage, collision, you need to define also some cryptographic test functions. And it is a hot topic for us. We study with our PhD students about designing new tests regarding this. Thank you very much.